Hi folks, this is going to be the fourth and final lesson on magnetism, and in this we're going to look at the motion of a charged particle in a magnetic field. Now I realise you'll have done this with Mr. Forwood in a previous lesson last year probably, but just for completeness I'm going to go through the learning intentions that first of all that we have, and then the main lesson for the electromagnetism unit. They should tie up with each other, and nothing that we're going to do should be particularly new to you. But here we go. So the learning outcomes that we're going to look at is 13.21 and 13.22. 13.21 says I can explain the helical path followed by a moving charged particle in a magnetic field, and then after that we can use relationships to solve problems on the force of a current carrying wire, which we've already done in lesson 3, and then the forces acting on a charged particle in a magnetic field. So here we're really focusing on an individual charged particle in a magnetic field as opposed to current moving through a wire. So charges moving in a magnetic field, we're going to start off in a very similar way as we did for the current flowing through a wire in a magnetic field. So if you remember, in that we had our magnetic field like so, and we had a wire, and this wire had a current flowing through it. We say that our magnetic field was like so. Then we're going to use the right hand rule in this case. So the right hand rule would then, we could go like this with FBI and determine the force. So B would be going from left to right across the page. I is like that. So in this case, if we're going to let's come here. We can see that with our magnetic field going left to right, the current going upwards, then the force that we would have would be coming out of the page. And so this wire as a whole, and if we're going to assume that the wire is a rigid thing, then the wire itself is going to pull up from the page. It's going to experience an upwards force. And we determined a formula to look at this. It was F equals IL B sine theta. The sine theta, of course, in this case would just be 0, would be 1, but the sine theta would come into play if you had a force that was making an angle with the direction of the magnetic field, where you would have 90 degrees, and if it was parallel you would have 0 degrees. And so in this case we've got right angle with the field, so your sine theta is 90 degrees, sine 1, sine 90 would be 1, which would just cancel out, leaving F equals ILB. Now if we take a similar scenario to this, but rather than look at a wire, let's just focus, and again let's just focus on if we have an individual electron. So let's have an electron, just say here, an electron with a charge of Q, and that's been fired through a magnetic field. It can have the same magnetic field as we did before. Now if you actually think about what current is, and current in a wire, current is the flow of charge per unit time. And so if we've got current, we would have, that is the flow of charge. Again, my Q's are terrible. So the flow of charge per unit time, I equals Q over T. And so what we have here is, with an individual electron, if an individual electron travels a distance through the magnetic field of L, just as we had the length of wire within the magnetic field, then we'll have the same formula. We have the force that this electron will experience will be I, which is the charge per unit time, or what we could say is that the time taken for the charge to move from this point to this point. In that distance, the strength of the magnetic field, and then I'm going to leave sine theta out for just now, but sine theta can just be put in here, put back in here at any time, and I will put it back in a second. Now, if your current for this is Q over T, I is equal to Q over T, and we substitute this in here, then we get F is equal to Q over T times L times B. And if the particle here, if the electron is moving a distance in a time, and then we can work out velocity just from length and time. So we also have velocity is equal to distance over time, but if we just call a distance, the distance that it travels, we're defining as L in this case. And so F will equal to Q times L over T times B, which gives us F is equal to Q V B. And so this would be our formula for a particle that's moving with a given velocity through a magnetic field, the amount of force that it would be subjected to if it's moving perpendicular. If it's not moving perpendicular, then we would just add in the sine theta at the end. So Q V B sine theta. So let's look at a worked example here. We have a proton moving in a magnetic field of strength 600 milliteslas. If the velocity of the proton is 4 times 10 to the 6 meters per second, calculate the force on the proton, and we're also wanting to state which direction this force will act. So if we are going to say, well, what I should have done in the question is have a diagram. We're obviously going to assume in this case that the proton is going to be moving perpendicular to the field. And so we have the velocity of the proton. A minute, I need to see this here. Technology. Right. So our velocity of our proton is going to be 4 times 10 to the power 6 meters per second. We have the strength of the magnetic field. We have a charge of our proton, which is no problem, and then we can solve. So we're just going to use just this. It's perpendicular, so we don't need to include sine theta. F equals QVB. Charge of a proton is 1.6 times 10 to the minus 19 times 4 times 10 to the 6 times 600 milliteslas, so that would just be 0.6. Which would give us 3.84 times 10 to the minus 13. Newtons. Okay, so that gets us the magnitude of the force. Now the direction it would take. So we have a positive charge. With a positive charge, you're going to be looking at the left-hand rule. So you use your left hand, fingers arranged as so, FBI. B, the magnetic field is going to be going from left to right. The direction of current is going to be in towards the screen. Direction of current is going to be, as I'm looking at in my paper, and so let's it this way. So B, then I don't know if you can see this, and then so you're going to have into the screen. And the force is going to point into the screen. And this is going to be the opposite from the examples that we used here and here, where we had a negative charge and you had it coming out. Everything the same, it will reverse the direction of the charge. So in this case, you're going to have the proton experiencing a force going into the page. And so we'll just add that on to the end, into page. Okay, so down that way. So we know that our proton, as it's moving through the our proton, as it's moving through the magnetic field, is going to experience a force going down into the page. And it's difficult to look at this in a two-dimensional sense, because what essentially is happening is a three-dimensional thing. But if the proton is here, then it's going to be experiencing a downwards force. Now, if we were to just sort of flip this around, I guess the best way would be to think about this in a slightly different sense. So if we have our magnetic field that is coming out of the page, so we're going to represent this by a series of dots. That should do. And our proton is moving in this direction. So our proton is here, is moving in this direction, and it's in the magnetic field. I am aware that that it's already entered the magnetic field, and as soon as it enters the magnetic field, it would start experiencing a force, and so it would start doing something different. But I'm conveniently just going to go with right there, because, well, it's, as I said, it's already hard enough to explain. I'm going to try and get, with my limited drawing skills, what we do. So we've got a proton. We're going to use left-hand rule, left hand, FBI. So B is coming out of the page, and so for you that's coming straight toward your face as you're looking at it on the screen, but because I'm looking on paper, it's going straight up in the air. Direction, so we're going to have direction there, and you can see that the thumb here, so B out of page, I, and then the thumb is going to be at this angle. So the point here where we're just going to start observing it, this particle is going to experience a force at right angles to its motion there. So this is going to start the particle to turn and to move in a curved path, and so it's going to start to move like this. But if we're looking at our, right, so yep, we're getting here. Let me just try and do this. This is so much easier if I'm standing in front of you waving my arms around like a balloon. But here we have the original motion of the particle with the magnetic field and the force. But as we start to turn that, you'll see what happens to the force. I'm just going to get rid of the B finger just now. And you're going to have this constant right angle, and as soon as we start to turn, you'll see that the force is always remaining at 90 degrees to the motion of the particle. And so by the time we get here, it's now still experiencing a force at 90 degrees, but that 90 degrees is pointing in that direction. And so it turns a bit more. And as it keeps turning, we're always going to get this force acting at 90 degrees, and it's going to be in towards the center of a circle. Circular motion, where the force is always acting in towards the center of that circle. Wait a minute, that's called centripetal force. That's what causes circular motion in the first place. And so if we treat the force that's being applied to this particle, which remember was F is equal to QVB, but it's causing circular motion, and force or the centripetal force, is going to be mv squared over r. Now to find the radius of the curved path, I'm just going to equate the two forces, solve for r, and there we go. So velocity here, gets rid of the square, and gets rid of this. Take r up here and qb down here, cross multiplying, we're left with r is equal to a little bit of a brain freeze. R is equal to mv over qb. So this will tell us the radius of the curved path, given the mass of the proton, which we know, the velocity of the proton, which we would know as well, the charge in the magnetic field or the magnetic induction. So let's just go and work out what the radius of the curved path for our example on the previous page would be. And so radius, so what did we have again? Well, we had 4 times 10 to the power of 6 meters per second. Let's see if I can remember all of this. We had 600 milliteslas, 0.6 teslas. We have the mass of a proton. Oh, goodness me. Mass of a proton. P is 1.673 times 10 to the minus 27. I actually had to go and look that up, and I forgot. So kilograms. So we've got mass, we've got velocity, we have the charge of a proton, which is obviously a fundamental unit of charge, and we can determine radius. So just substitute all of these values in. So we substitute the numbers in, and we can type them into a calculator, and that will give us 0.07, let's call it 0.07, so we could say 7 centimeters. So the radius of that curved path, the proton is going to move around here, and the radius there would be 7 centimeters. Okay, so we'll look at another worked example. In this case, we have an electron entering or in a magnetic field that is moving from left to right. The electron is moving, is entered an angle, and let's call the angle here, as if we say, so we're going to go, so at an angle of 60 degrees. Okay, so now if it enters with an angle of 60 degrees, what we can do is, if we just take this electron over here, we'll have 60 degrees there. Now we can split up the force, so this is going to have a force that's being applied to it, but we can split this force up into 2 separate components. We'll have a force that's perpendicular, so that's going to be perp, and there'll also be a component of force that's parallel. And so the force that's perpendicular, so F perp will be F sine theta, which is where we get our F equals QVB sine theta. But our force parallel is going to be F cos theta. Similarly, if it's moving with a velocity of v, so it's got a velocity of v, then the v perpendicular is going to be v sine theta, and its parallel component of velocity, v parallel, is going to be v cos theta. So if we know the velocity that this particle is traveling at, then we can calculate the radius of the curved path that it's going to be moving in. So in this case, we're going to have right-hand rule, FBI, so B is this way, and we're going to have, it's like you can't actually see what I'm doing here. And so your B is going to be there, your I is going to be like that, and so it's going to be experiencing an upwards force in this case. It's going to be an experience, the upwards force that is caused by the perpendicular component of the velocity. So this is, and I'm sure you know where I'm going with this. And so the particle, as if it's here, it's going to be traveling along and it's going to be experiencing an upwards force, and so it's going to start traveling in a circle that looks like this. So here it enters the component of the perpendicular component of the velocity is going to make it turn in a circle like this. And that can be found, so as before, we would just have R is equal to mv over qb. So this will give us the radius, but our velocity here must be the perpendicular component. And so that would be v is equal to v perpendicular, which we're going to say is v sine theta. So we could really rewrite that just to v sine theta over qb. And so in this case, we would have sine theta at 60 degrees and everything as before. But something else is going to happen. It's going to experience a force like that, but it also has, while it's doing this, a parallel component of velocity. And so as it's moving in a circle perpendicular to the field, it's going to have a component of velocity which is going to make it move from left to right as well. So what you're actually going to get is you're going to get this helical motion. So helical motion will be like the motion of a spring, if you imagined that a particle is following a path around a spring. And we can tell how much that motion is, how much that left to right motion is, with something called the pitch. And to work out the pitch, we need to know a couple of things. And so we're going to have, let's see if I can try and draw this now. So it's going to move up and around and like this. So one full circle for this, it goes from here up and down and around, and it gets to that point there. Now that is one complete revolution as done by this, and that will happen in a time, so one revolution in a time of t, like the period. And the distance that it's going to move, so this, the distance, which will be the pitch, so the pitch is defined as the distance it moves, in this case from left to right, in one revolution, is going to be the speed that it moves parallel, so v parallel times period, i.e. the time for one revolution and the parallel velocity. And our parallel velocity is v cos theta, so v cos theta times period. Okay, so the period, now the period is going to be determined by the perpendicular velocity of this. And so if we remember back to the start of Unit 1, we had our angular velocity was defined as the number of radians in one revolution, i.e. 2 pi radians, divided by the periodical time t, and also your angular velocity omega is equal to excuse me, v over r. V equals r omega. So we have these two equations here, and if we bring both of these together, then we can find out what t is, because remember we know this v. This v is the v perpendicular. Okay, so we can substitute this in here. So v cos theta times t, rearranging that would be 2 pi over omega. This is going to be then omega is v over r. Omega, so v cos theta, so v cos theta is the v parallel times 2 pi, and that's the inverse, and so that will be the inverse, so 2 pi r over v. Oh, we've lost the bottom. So 2 pi r over v, but this is the v perpendicular, and it's v cos theta times 2 pi r over v perpendicular would be v sine theta. Okay. And then v cos theta, or cos theta, divided by sine theta would be 1 over tan theta. And so this would give us v cos theta over v sine theta times 2 pi r. The v's will cancel each other out. This will turn into 1 over tan theta, and eventually the pitch, sorry, I keep falling off the end, but I will stop soon. So the pitch is 2 pi r over tan theta. So knowing the radius of the curvature of this will be able to work out the pitch as well. Of course, you don't need to do all of this. You can work it out piecemeal and individually if you want. You can certainly go back to just here. If you know the perpendicular velocity, so let's start from there. V perp is equal to r omega, which would be 2 pi r over t, and so your period, which is the crucial thing because you're going to use the period with the parallel component of velocity, would just be 2 pi r over v perpendicular. So it might be a sort of easier way to work out the pitches if you just work out the horizontal, not the horizontal component, the perpendicular and parallel components of velocity of this. You can get the period from the perpendicular velocity, i.e. how fast it's moving in the circle. From the period, then you can just go straight back up to that one to get the pitch if you know v cos theta times period, which would give you which you could use from there. Okay, so that concludes all of the lessons in magnetism, and there's 4 of them. As ever, any questions, please just ask, and thanks for watching, and I'll see you soon. Okay, bye.